Welcome. Today, we're going to tackle a fascinating problem that might not look like your typical algebra equation. Our goal is to find the value of x that satisfies the equation 5 to the power of x minus 4 to the power of x equals 9. The fact that the exponent is the variable we're trying to solve for makes this a bit tricky. We can't use our standard logarithm rules right away because of that subtraction sign. In this video, you will learn a powerful technique to solve equations where logarithms don't directly apply. You'll see how to leverage function analysis and the concept of monotonicity to find solutions. This method will allow you to solve equations that seem to defy standard algebraic methods. Let's begin by seeing why our standard tools might fall short. Our objective is to first understand why this equation is not as straightforward as it seems. Let's rewrite the equation as f of x equals 5 to the power of x minus 4 to the power of x minus 9, and our goal is to find x such that f of x equals 0. A common first instinct is to try and use logarithms, perhaps by isolating the terms. This would look like 5 to the power of x equals 4 to the power of x plus 9. If we now try to take the logarithm of both sides, let's say the natural logarithm, we get the natural log of 5 to the x equals the natural log of the quantity 4 to the x plus 9. We know a property of logarithms that allows us to bring the exponent to the front. This gives us x times the natural log of 5 on the left side. But notice, we cannot do the same thing on the right side. The logarithm of a sum, ln of a plus b, is not the same as ln of a plus ln of b. We are stuck with x on both sides, inside and outside the logarithm, making it impossible to isolate. This shows that a simple algebraic solution using logarithms isn't going to work for this type of equation. So if algebra isn't enough, what's our next step? The key to solving this problem lies in analyzing the behavior of the function involved. Our objective in this scene is to analyze our function f of x to determine where it's increasing or decreasing. Let's recall our function f of x equals 5 to the x minus 4 to the x minus 9. The primary tool for analyzing function behavior is the derivative from calculus. The derivative of f of x, written f prime of x, will tell us the slope of the tangent line at any point x. Remembering the derivative rule for an exponential function, the derivative of a to the x is a to the x times the natural logarithm of a. We can find our derivative. The derivative of 5 to the x is 5 to the x times ln 5. The derivative of negative 4 to the x is negative 4 to the x times ln 4. The derivative of the constant negative 9 is just 0. So our derivative is f prime of x equals 5 to the x times ln 5 minus 4 to the x times ln 4. Now we need to determine if this derivative is always positive, always negative, or if it changes sign. A positive derivative means the function is increasing, and a negative derivative means it's decreasing. We need to compare the two terms in our derivative, 5 to the x times ln 5 and 4 to the x times ln 4. The natural log of 5 is approximately 1.6, and the natural log of 4 is approximately 1.4. This means f prime of x is roughly 1.6 times 5 to the x minus 1.4 times 4 to the x. For any positive value of x, the exponential growth of 5 to the x is much faster than 4 to the x. This dominance means the first term will be significantly larger than the second term, so their difference, the derivative, will be positive for all x greater than 0. What about negative values of x? Let's write x as negative a, where a is a positive number. F prime of negative a is 5 to the negative a times ln 5 minus 4 to the negative a times ln 4. This can be rewritten as the natural log of 5 over 5 to the a minus the natural log of 4 over 4 to the a. For a greater than 0, 5 to the a is larger than 4 to the a. And since the natural log of 5 is larger than the natural log of 4, the first term in this expression will always be greater than the second term. Therefore, the derivative is also positive for negative x. This is a profound discovery. The derivative f prime of x is always positive, regardless of what x is. This means our function f of x is always increasing. A function that is always increasing is called monotonic. This monotonicity is our key. A function that is always increasing can only cross the x-axis, and thus have f of x equal to 0 at most once. It cannot go up, come back down, and go up again, so it cannot have multiple solutions. We have successfully shown that there can be at most one solution. Our next objective is to find that unique solution. When a problem guarantees a unique answer and we can't find it directly, the next best strategy is often to test some simple values. Let's return to our original equation. 5 to the x minus 4 to the x equals 9. Let's try testing some integer values for x, starting with 1. If x equals 1, the equation becomes 5 to the 1 minus 4 to the 1. This is 5 minus 4, which equals 1. The result is 1, not 9. So x equals 1 is too small. Since our function is increasing, we know we need to try a larger value for x. Let's try the next integer, x equals 2. If x equals 2, we have 5 squared minus 4 squared. That's 25 minus 16, which equals 9. And there we have it. We found the solution. When x is 2, the left side of our equation, 5 to the x minus 4 to the x, equals the right side, which is 9. Let's put all the pieces together and see the full argument. Our objective is to recap our method and visualize the solution. We started with the equation 5 to the x minus 4 to the x equals 9. First, we showed that standard algebraic methods with logarithms don't easily solve this because of the sum of terms inside a logarithm. So we created a function f of x equals 5 to the x minus 4 to the x minus 9, and our goal was to find its root, or where it equals 0. Next, we used calculus to find the derivative of our function. We found the derivative to be f prime of x equals 5 to the x times ln 5 minus 4 to the x times ln 4. By comparing the exponential terms and the logarithmic constants, we proved that f prime of x is always positive. This positive derivative means the function f of x is always increasing or monotonic. This is crucial. An always increasing function can cross the x-axis at most once. Therefore, there can be at most one solution to our equation. Finally, we used this guarantee to simply test some integers. We found that x equals 2 makes the equation true. Since we know there's only one solution, this must be it. So the final answer is x equals 2. To visualize this, imagine the graph of f of x equals 5 to the x minus 4 to the x minus 9. The graph starts very low, increases steadily, and crosses the x-axis exactly one time, at the point x equals 2. This visually confirms our analytical solution. Let's quickly recap what we've accomplished and what we've learned today. We began with a seemingly complex problem, 5 to the x minus 4 to the x equals 9, which couldn't be solved with basic algebra or logarithms. You learned a powerful two-step method to tackle these types of transcendental equations. First, we used calculus to show that the related function, f of x, is monotonic, which guaranteed the existence of at most one solution. Second, armed with the knowledge that our answer was unique, we used simple substitution to find the answer. X equals 2. This approach of combining calculus to understand a function's behavior and then using that knowledge to find a solution is a fundamental technique in mathematics. I hope this was helpful.